All right, super. So we're really delighted to have Matt Sievert here to talk to us about dissecting the guts of the proton. So Matt is assistant professor at New Mexico State University. He received undergraduate degrees from Virginia Commonwealth University in physics and Spanish. Hola.
Hola, ¿qué tal?
That's the extent of my Spanish. And then a master's degree in physics in 2007. As mentioned earlier, he received his PhD from the Ohio State University under Yuri Kopchegov, who both Herbert and I know very, very well, and then was a postdoc at Brookhaven National Lab, Los Alamos National Lab, Rutgers University, and UIUC, University of Illinois Urbana-Champaign, where the last move was a lateral move due to the whole group moving, before landing, as mentioned, at New Mexico State University. So Matt is just one of those world experts in small x, high energy physics, quantum field theory, strong force, all of these wonderful things. Yeah, I think I covered everything, Matt.
Yeah, I think so.
Super. So yeah, please take it away.
Fantastic. Thank you so much for the invitation, Will. It's a pleasure to get to speak to all of you today. I'm going to minimize my view of the camera of the audience so I can see what I'm pointing at, but please, if anyone has questions, feel free to speak up at any time. Feel free to interrupt me and we can discuss. So my understanding is that this talk is one of two, and my intention is that this talk is sort of a colloquium level overview, sort of an invitation to high energy QCD in general. And next week, I'll talk about a more specific project relating to asymmetric transverse momentum drift of jets moving through something like flowing quark-gluon plasma. So feel free to jump on in. I want to make this as accessible to students as possible. So the title is Dissecting the Guts of the Proton. And really, I want to talk about the two ways that we have to look inside the structure of the proton. And that falls very loosely into two categories, one of which is conventionally referred to as hot QCD. This is where we try to understand the structure of what's inside the proton by melting it, essentially, by creating a thermodynamic environment with temperatures so high that the proton and neutron melt into their constituents, which are quarks and gluons, that are then free to flow around like a deconfined fluid. That's sort of one method, the high temperature method of looking at what's inside the proton. The other umbrella is what you might call cold QCD, and this is essentially looking at the proton in situ, which is using a kind of electron microscope, which is really a collider at these energies, to directly resolve the structure of the proton as it is in the proton without heating it up and causing it to melt first. So that's the sort of overview. As an introduction to what QCD is, the theory of the strong force, I always really like to start by comparing two bound states that are well known to us, the proton and the atom. The atom, of course, is not a fundamental particle. The atom is a composite particle in which the constituents, which are protons, neutrons, electrons, are bound together by the electromagnetic force, that it's really the Coulomb potential of negatively charged electrons being attracted to the positively charged nucleus that hold the electrons in their stable orbits. And that's what determines the chemistry of the atom. Everything that we know about chemistry comes from the structure of the atom, why the atomic orbitals are the way they are. And as we know very well, the structure of the atom is a very deep reflection of the fundamental physics of the electromagnetic force, the fine structure, the hyperfine structure. Structure of the atom teaches us about the fundamental physics of the electromagnetic force. And in exactly the same way, the proton is also not a fundamental particle. Although it was believed to be for a long time, the proton is now known to be a composite particle, much like the atom. It's a bound state of, in the simplest picture, three valence quarks who are interacting now not according to the Coulomb potential, but primarily according to the strong force potential, the nuclear force. And very similarly to the atom, the structure that appears for the proton, all of the orbitals, if you like, or all of the chemistry, if you like, of the internal structure of the proton is similarly a deep reflection of the physics of the strong force, which is really what we want to understand better. So it's no accident that both the proton and the hydrogen atom, the structure of the atom, were discovered simultaneously, and they were both discovered about 100 years ago. So the baby pictures of the proton and the baby pictures of the atom were really born in the Rutherford Gold foil experiment, which is an experimental setup that we'll come back to at much higher energy scales a little bit later. It's essentially a collider experiment, just at relatively low energies. It's a collider experiment that uses a radioactive source of alpha particles. And what you look for is those rare events when the alpha particle doesn't do the normal thing, where it goes straight through or with a very small angle deflection. You're really looking for the incidence of backscattering, deflection at very high angles, because the high momentum transfer between incoming momentum and outgoing momentum, that high Q value tells you that you're really measuring some short distance structure in the gold foil. So if you want to discover the existence of the nucleus, you need to really look for hard backscattering events in your collider. And that's really all the Rutherford gold foil experiment was. So that gave the evidence that there is a tightly bound, positively charged core inside the atom, which carries all of the positive charge. And then that directly led to the Bohr model of the atom, where you have the proton or the nucleus concentrated in the center and the familiar orbital structure that comes out. Of course, we know that this is just the starting point. This is just the baby pictures. And in the past 100 years, the atom has completely grown up. So our understanding of the electromagnetic force, our understanding of the microscopic quantum structure of the atom is so advanced that we literally use it as the definition of time itself. What I mean is that we can compute and measure with such extreme precision the hyperfine splitting of the ground state of cesium-133 that the frequency of that transition is used to define the second, according to the US National Institutes of Standards and Technology. That is the most precise extraction of fundamental constants used to define the second that we have. So altogether, this is a combined fractional certainty of less than 1 part in 10 to the 16 or 10 to the 15, which is insane. Similarly, the theory is so advanced that you can calculate up to something like 1100 digits of precision. This is just one particular example. 891 four-loop Feynman diagrams to the electron G-2, the anomalous magnetic moment. So all of this is just absolutely mind-blowing to me. This is astronomical precision. We understand the structure of the atom so incredibly well, which is why it's ridiculously striking how much we don't understand about the proton. Whereas we understand the structure of the atom to insane precision, we don't understand even where basic overall properties of the proton come from in terms of their microscopic constituents. So these are just 3 examples of macroscopic properties of the proton that we do not understand. The origin of the proton spin in terms of fundamental quarks and gluons is a very long-standing puzzle that we don't understand. The proton radius isn't working out right. Depending on how you measure it, you get one answer or another answer. That could either be an indication of interesting nuclear physics going on, or maybe interesting particle physics going on, if it's really true that muons see a different radius of the proton than electrons do. And the origin of the proton mass, something close to 1000 GeV, starting with elementary quarks that are almost massless, only a couple of MeV each. The origin of the proton mass is one of the millennium problems. So if you can sit down with the QCD Lagrangian and prove that you get a proton out of it with a mass almost of 1000 MeV, you instantly win $1 million, because that's one of the millennium problems. So the comparison is that while the hydrogen atom is a completely grown-up, sophisticated professional, the proton is sitting there being a moody teenager saying, "You will never understand me." And the reason for that vast discrepancy between what we do understand about the atom and what we don't understand about the proton comes from the fundamental structure of the theory itself. Essentially, it's the statement that E and M, Maxwell's equations, or QED, is a linear theory. So that before one starts to include quantum loop corrections and all of that interesting stuff, you have a very nice superposition principle. And this is completely familiar to us, that if you have light from one lamp, light from another lamp, the light doesn't bounce off each other. The light just adds together constructively. And so you get electric field of the first guy, electric field of the second guy, and the total intensity comes from the electric field of the sum. And the reason that you have this very simple superposition principle is because in E and M, there is only one kind of charge. I would say electric charge is a scalar quantity. It might be positive, it might be negative, but it doesn't have a direction associated with it. And that's what gives you all of the structure of Maxwell's equations. There is exactly one difference between E and M and the strong nuclear force, which changes absolutely everything. And that one difference is that in QCD, the theory of the strong force, color charge is a vector. That means that it doesn't come in only one type. It comes in three linearly independent types that we conventionally call colors: red, blue, and green. So it's exactly like having three independent axes of color that have different types of charge in them. And because now you have a vector, you have the ability to rotate between different components of the vector. So you can start with something which is pointing in the red direction and perform a rotation on it to end up with something pointing in the green direction. And that change from scalar charge physics in QED to vector charge physics in a non-abelian theory like QCD destroys the linearity of the theory. Essentially, if I start off with a particle that has color red and I radiate something and I end up in a state that's color green, that thing that I radiated has net color. It has the difference between what I started with and what I ended with. So because there are multiple types of color and you change them when you emit a particle, you emit a gluon in this case, that means that the gluons are charged. They have whatever charge is the difference between where you start and where you end. And since the radiation itself is charged, that leads to vastly different implications. So for instance, the superposition principle of E&M works because the photon is not charged. It's electrically neutral, so that you can add up one photon plus the other photon and they don't see each other, at least until one loop in QED when the photon might fluctuate into charges. Whereas in QCD at tree level, there's a direct coupling between this charged gluon, that charged gluon, and it's exactly like they bounce off each other. There is a gluon-gluon scattering cross-section at tree level in QCD that you can calculate. So the fundamental difference is the nature of charge in the two theories. Both of them are structurally very similar theories that look like Maxwell's equations about how source charges radiate fields in a relativistically covariant way. But that one change about the nature of charge leads to nonlinear self-interactions of the gluons, and those nonlinear interactions with of the gluons change the structure of the potential completely. We see the familiar sort of Coulomb tail in the heavy quark potential at very short distances. So this is the effective potential between a quark and an antiquark that are very heavy and that are sitting fixed in space. So at very short distances, you see the attractive Coulomb potential, the 1 over r. But instead of leveling out to 0, the way that the Coulomb potential does in the hydrogen atom, this one grows and keeps on growing. Instead of flattening out to 0, which means that the force, the derivative of the potential, goes to 0, here the potential levels off to a straight line. And the slope of that line is constant. So this region out here, the confining potential is well described by a slope times the distance. And if you calculate the force, then that's just this constant sigma. Sigma has the name of the string tension. That's the effective force between a quark and an antiquark. The number that you get for that slope is pretty close to 1 ton. So the answer is between a quark and an antiquark, as you start pulling them apart, there is 1 ton of force that never gets smaller, no matter how far apart you pull them. And that's the fundamental difference. That's the part that changes all of the implications of QCD compared to QED. What this means is that it's much harder to measure the structure of the proton than it is to measure the structure of the atom. Because to measure the structure of the atom, all you have to do is liberate an electron. You can ionize an electron out, you can measure how much energy it took, how much momentum it absorbed, and you get a direct imaging of the density of states of the hydrogen atom, or whatever atom you're talking about. But you can't do anything like that for the proton. If you try to take something like, I think here in this cartoon, it's a pion, but you can take a particle like the proton and you can try to pull a quark out of it. But if you do, you're putting in 1 ton of force to separate the quarks, and that force never gets smaller. Eventually, you put in so much energy, so much work trying to separate the 2 quarks that it becomes energetically favorable to create new quark-antiquark pairs using E equals mc squared and end up with 2 bound states. So you, instead of ever being able to take the bound state and rip one of the constituents out, here you start with a bound state, you try to rip a constituent out, but you end up with 2 bound states in the final state instead. The situation is very analogous to what happens if you try to take a bar magnet and break it in half to try to isolate a single magnetic monopole. No matter what you do, how many times you break the magnet in half, you always end up with a bound state of a north and a south magnetic pole. So in a very similar way, the fact that you can never get a magnetic monopole due to the nature of the magnetic field, you can never get a single isolated quark due to the nature of the strong force. And what that means is that you see very, very different things when you look at a process that's mediated by QED, electromagnetism, versus when you look at a process mediated by QCD, the strong nuclear force. Electromagnetic processes are super clean. This is an example of an event display from the Opal detector at LEP, the Large Electron-Positron Collider. So this was a case where the electron and the positron were coming in along the beam axis here into the page. There's a collision that happens right in the center. And what this is showing is an event display that detects 2 tracks and 2 energy depositions in the calorimeter. This is a super clean electron-positron goes to mu plus, mu minus process that you can calculate at tree level in QED. Absolutely beautiful, and the comparison with tree level QED works way better than you would even expect. But contrast that with what happens if you collide 2 protons together at the ATLAS experiment. You get a whole slew of particles that comes out. This is a direct reflection of what happens when you hadronize particles. If you have some kind of hard scattering event, if you actually succeed in breaking the proton apart, you don't see the individual quarks that you would like to. Instead, you see all of the fragments that get created when each one of those quarks fills up the vacuum with other particles to assemble bound states. So the one difference structurally between what QED is and what QCD is leads to radically different consequences for the theories, even though at a fundamental level, they're very, very close to each other. So with this in mind, the question that I want to answer in this talk is, how do we learn about the structure of the proton? How do we successfully break apart the proton to see what's inside of it? And the first way that we have to do this is by heating it up. So like I mentioned in the beginning, if you take the proton and you heat it up to a sufficiently high temperature, you expect to melt the bound state and see something which is more indicative of the underlying degrees of freedom. As soon as you start talking about temperature, you also start talking about time. That's because as you go back in time cosmologically to the very early universe, the time scale is directly related to the temperature scale. So if you look back early in the early universe, for instance, most people are familiar with the cosmic microwave background. The CMB is created in the early universe by the formation of neutral atoms. That you had an early epoch of the universe about, let's say between 3 minutes and 400,000 years of the early universe, between temperature scales of 10 to the 9K and 10 to the 3K. Above this transition temperature, the early universe was in the state of an electromagnetic plasma. And that plasma was opaque to light because of all of the charges that were moving around. But the very first time the early universe cooled far enough that it formed electrically neutral atoms, then for the first time, the universe became transparent to light. And what happens is that whatever the thermal light that there was in the plasma phase, at freeze out or at formation of neutral atoms, that light is released. And then it essentially propagates freely through the universe. And that is what we now measure today, 10 to the 9 years compared to 10 to the 5 years. That's what we measure as the cosmic microwave background. And it carries information about that early plasma phase of the universe. In exactly the same way, if you go back a little bit earlier, 10 to the minus 4 seconds to a temperature scale of 10 to the 12 seconds, you have a very similar phase transition between an extremely high temperature state in which the protons and neutrons have melted to the very first incidence of formation of color neutral proton and neutron states. So in exactly the same way that one has the electromagnetic plasma transition in the early universe that led to the cosmic microwave background, there was also a nuclear plasma transition around 10 to the minus 6 seconds that characterized the formation of protons and neutrons for the first time. So when experimentally we try to recreate this quark-gluon plasma at something like the LHC, we often talk about it as a way of looking back into the early universe. And this is why, that we're recreating temperature conditions that were not present anywhere in the universe until now, since 10 to the minus 6 seconds after the Big Bang. So when you create the quark-gluon plasma and you look at the signals that come out of it, there are essentially 2 defining features that we see. The first is that when you create the quark-gluon plasma, you get a huge number of soft particles that are coming out. Those are represented by these tracks or these tracks. And those soft particles all behave in a very similar way. They behave as if they are flowing together as a fluid. And that the flow of the soft particles is very well described by a hydrodynamic theory. So the first canonical signal that you measure when you look at heavy ions is collective flow of soft particles, particles that have relatively low energy. So let's say less than a GeV or so. And the flip side is if the soft particles, the low energy particles, are creating this thermal bath of the plasma, the high energy particles are not a part of the plasma. They are foreign objects that are penetrating through the plasma. So if in addition to the soft background, you create a hard scattering event that generates two very high energy particles, those high energy particles might emerge as jets or individual high PT hadrons that you measure. The jets are high energy particles that then propagate through the plasma lose energy. We see a very strong signal that the number of high energy particles that you create in thermal background is much less than if you created those particles in vacuum. So we see evidence that, for instance, if you create two of them, one of them might escape and you detect its energy in the calorimeter. The other one, as you might notice, gets a little bit deflected. For one thing, this jet and that jet are not exactly back to back. And you see that some of the energy is lost, some of the energy is quenched, so that the total energy in these towers is less than the total energy in those towers, and that the reason is essentially that the energy is being spread out over larger angles. So the essential idea here is that much like a bullet slowing down and being stopped as it moves through water, these high energy particles are slowing down, losing energy, and getting quenched or extinguished because of the strong interactions with the plasma. So little shameless self-promotion aside, the two main observables, the two canonical signatures that we have successfully made the quark-gluon plasma are collective flow of the soft sector and quenching of the hard sector. The reason that collectivity or collective flow appears in the soft sector is actually easy to understand. When we look at lots of different phenomena in physics, we see hydrodynamics everywhere. And the reason is that hydrodynamics is an effective theory. Hydrodynamics is something that's supposed to be a good description of the physics anytime the mean free path of whatever the fundamental particles interacting with each other are, as long as that mean free path is much smaller than the system size. Essentially, what that means is that all of the microscopics of the theory, everything that tells me exactly how two particles scatter off each other, those details don't matter. All that you really see over very long distances is overall conservation laws: conservation of energy, conservation of momentum, conservation of charge. And all of the microscopic details about exactly what theory that you're working with get encoded into the equation of state, transport parameters like the viscosity or the electrical conductivity. And so the hydrodynamics is sort of a universal effective theory that says, I don't care about the short distance stuff. All the short distance stuff I stuff into constants or input functions. All of the physics is just the physics of conservation laws. So that makes perfect sense in a situation that we expect to be very, very strongly interacting, such that the mean free path is very short. I should mention before I go on that this picture of hydrodynamics and where it comes from and why it works is the old picture of hydrodynamics. And there's been a lot of very interesting work in recent years that shows that even when you're far from this limit where you expect hydro to work, there are still interesting cases where hydro works. So there's a very interesting discussion in the field about just because hydro works well at describing heavy ion collisions, does that mean that you're actually in a canonical short mean free path phase? Maybe not so much. Maybe there's some exotic hydrodynamics that's going on. Okay, so in any case, the hydrodynamics that you have has an extremely nice or simple property, a simple mapping between whatever the initial shape of the plasma you created was and whatever that final momentum space flow that you measure in your detectors is. When I was at Rutgers, one of our students referred to it as nature's Fourier transform. And I think that's the perfect metaphor. That's essentially what happens, is that the high pressure gradients that are created in whatever your initial condition, the initial shape of the plasma looks like when it first begins to behave thermodynamically, whatever that spatial geometry is, gets converted very efficiently by pressure gradients into momentum distributions. So to a ridiculously good level of accuracy, which I'll show you in a moment, you can take your initial state, whatever the shape is, and just decompose it by Fourier series, decompose it into Fourier modes. And you can say, well, take this shape, how elliptical is it? This cosine 2 theta elliptical modulation of position space, that's what the ellipses are supposed to represent, gets transformed into a momentum elliptical anisotropy. That's what the arrows are supposed to represent. So if this is the shape of the initial state, the gradients of the initial state are the ones that point out along the short side, in along the long side. So those differences are what lead to an elliptical momentum pattern in the final state coming from an elliptical position distribution in the initial state. And the same holds for higher Fourier harmonics too. You can talk about the degree of triangularity of the initial state, which leads to a degree of triangular flow of the final state. And the conversion between whatever you had in the initial state geometry and whatever you measure in the final state momentum distribution, the conversion is extremely efficient because the interactions in the plasma are extremely strong. Those very strong interactions mean that the viscosity is very small. So that nature's Fourier transform has very little friction in it, very little loss between whatever you had in the initial state and whatever you have in the final state. So the point is that that's a double-edged sword. That's good because I would like to simply describe the complicated theory of hydrodynamics, but it's bad, it's hard because I want to measure things about the plasma, and the questions about the plasma are fundamentally entangled with questions about what was my initial condition. So often in this discipline, there's a lot of model dependence or assumption dependence about whatever you picked here in the initial condition, because you usually want to use that to extract things like transport properties of the plasma. Okay, so when you look at the heavy ion collision, what do you see? The very first thing that you see is the multiplicity distribution, just number of particles that are produced. So this is a histogram. I believe this is from Elise, although I left out the citation. Apologies for that. This is just an example of a histogram of how many particles that you make in arbitrary units. And so you see there's a large number of events that make a small number of particles, and then there's a decreasing number of events that make a large number of particles. But what one sees very quickly is that there's a super strong correlation between how many particles you make and the geometric shape of the event as measured by these anisotropic flow coefficients. So this is the notion of centrality experimentally, that it's very easy to just measure the number of particles that you see in your detector. And if you just break the number of particles down by percentiles, you say, find me all of the events that made the top 5% number of particles. That's referred to as the 0 to 5% centrality class. And there's a strong correlation that says the events that produce the most number of particles had the greatest overlap area. And if they've got the greatest overlap area between two colliding nuclei, that overlap area is mostly very round. So experimentally, it's very convenient to select on things like the number of particles or the centrality class, which is just a percentile ranking of the number of particles. But that's a great lever to use to select on events that are rounder, more central, or more elliptical, more peripheral. So we see that this correlation of geometry with centrality is very strong, and that's powerful because you can use that to make a selection cut on centrality and infer the geometric dependence of the event. So when you do this, this is where it really starts to matter what assumptions or what model you take for the initial state. The simplest possible thing that you can take is referred to as optical Glauber models. This is a picture where I have a smooth density for nucleus A, a smooth density for nucleus B, and then I combine them together somehow to construct the energy deposited in the overlap region. So the simplest version would be something like, oh, I've got a density profile, let's call it TA. I've got a density profile, let's call it TB. And you might do something like TA times TB or TA plus TB, or some simple way of combining the profile of nucleus A with the profile of nucleus B. If you do that, then you get a decent description of what the geometry should look like in the middle. And this smooth density picture nicely captures that correlation with centrality. It correctly describes the correlation of the overlap area and the number of particles with the overall geometry. That's because this smooth density is really like a mean field picture, where you say, I don't really care that much about the fluctuations inside each nucleus. I just know that overall everything is very smooth. This gets a lot of things right. It gets in particular the elliptic behavior correct, but it gets something else very wrong. In particular, it gets the triangular behavior completely wrong. And that's because this smooth model, no matter what you pick for nucleus A and nucleus B, if they're smooth density profiles, you always have an exact mirror plane between the left and the right. And that reflection symmetry makes it impossible to ever create something which is anti-symmetric, an odd Fourier harmonic. So the simple optical Glauber picture is a great starting point, but it doesn't go far enough because it cannot ever produce non-zero triangular flow, which is seen in data. It's smaller than the elliptical flow, but it's definitely not zero. So a smooth density profile is not an adequate starting point for your initial state. A much better starting point for your initial state is something that fluctuates, something that says, I know that my lead nucleus is not a smooth density profile, but it's made up of 208 individual protons and neutrons, each of which has a randomly fluctuating position. So you can change the details of how you mock it up. But if you put in fluctuating positions of the 208 protons and neutrons in nucleus A, fluctuating 208 protons and neutrons in nucleus B, and a systematic way of deciding which protons from A interact with which protons from B, that gives you what's referred to as the Monte Carlo Glauber model, where now you have a lumpy initial condition. And you see that that lumpiness of the overlap region breaks the perfect left-right symmetry due to event-by-event fluctuations. This is what produces something which is on average elliptical, the same way as this one, but significantly fluctuates. In particular, this event has the ability to produce a triangular initial state, which this one does not. So part of what we see is that that very close mapping between initial and final state allows you to put very serious constraints on the initial state that says, you can put in a lot of different theoretical ingredients for what you think is going on, but you must have these ingredients at least. Any theory that does not start with a fluctuating initial state is wrong. It cannot describe the systematics of the heavy ion collision. So this is just an example of the model discrimination power of heavy ion collisions. The situation is not hopeless. This is what leads to sort of the overall picture of the heavy ion collision, that we talked about the density profiles that you have of two nuclei that are about to collide. Here, the spherical nucleus in the rest frame is Lorentz contracted down to a pancake due to relativity. Then you have the overlap of those two profiles. That's what creates a particular initial state. And then after that first Fermi over C, where nobody really understands exactly how the initial energy gets deposited and becomes this quasi-thermal state, what we do know is that by about 1 Fermi over C, the system is well described by hydrodynamics. And then you can describe the evolution of that system even across the QCD phase transition. This is the hardest part of the theory, but hydro doesn't care. For hydro, this difference between the plasma and the hadron gas is totally encoded in the equation of state. It's all microscopics, and it's the same kind of fluid before and after. Eventually, the density and the temperature of the plasma falls so low that it no longer behaves like a fluid at all. Once the density is so low that the particles no longer rescatter off of each other, then they just continue along straight line ballistic trajectories. This is referred to as freeze out. And at that point, the individual particles fly forward and then they're picked up in the detector. So the experimental problem of looking at the final state particles and trying to infer something about either the transport coefficients in this phase or the initial conditions in that phase is a very difficult multi-scale problem to try and disentangle. So it requires looking at a lot of different observables that are sensitive to different timescales. I referred to hydrodynamics as nature's Fourier transform, and this is what shows it. This is a comparison from a set of actual hydrodynamic simulations done by my former boss, Jackie Noronha-Hassler at UIUC, where you start off with a particular lumpy initial condition generated by something similar to Monte Carlo Glauber. You allow it to run and solve the hydrodynamic equations of motion, and you see how, as a function of time, that elliptical shape with the long side in the y direction gets gradually converted into an expanding ellipse where the momentum, the direction of expansion, is primarily along the x direction. And you can quantify and correlate those things with each other if you have the full theoretical description of the hydro. So I can take my Fourier coefficient that measures the ellipticity of the initial geometry. I can similarly take a Fourier coefficient that measures the ellipticity of the final state momentum distribution, and I can measure the correlation of those two quantities. That's what this is. This is referred to as a Pearson correlation coefficient. When this number is close to 1, it means that this final state ellipticity of momentum is perfectly correlated with the initial state ellipticity of position. And when it's close to 0, there's no correlation. And what you see is that this correlation coefficient is very close to 1 for a wide range of collision systems for a wide range of centralities. So despite the fact that there's a huge amount of physics going on in here, I, as a non-hydro expert, am grateful because this means that I don't need to know everything about the microscopics, because to a fantastic degree of accuracy, hydro is linear response. If I know the initial condition, I can just multiply by a proportionality coefficient and skip all the hydro to go directly from the initial condition to the final state. And if, linear response isn't good enough, if I'm in this region, then we know how to systematically correct that to include the effects of cubic response or higher orders. So despite all of the complexity, nature's Fourier transform really just preserves simple aspects of the initial state and maps them to the final state. This is a chance for me to highlight some of the recent work that I've been involved in looking at the initial state. One thing that I'm very excited about is looking at contributions to the initial state beyond just the energy density. What is standard procedure in the field is to calculate an initial state that looks like this, where you have a lumpy distribution of your initial energy density. But the energy density isn't the only thing that we evolve with the hydro equations of motion. Hydro equations of motion also evolve charge densities. And most of the time, when we're thinking about quark-gluon plasma at the LHC, high energy collisions don't leave any charges overall inside the plasma. We expect that overall the total baryon number, total electric charge, total strangeness of the initial condition should be zero. Q total should be zero. And so most simulations in the field look like this, where you say, I have something for the energy density, here's what the profile looks like, and I take everything else just to be zero. That makes sense at the level of the total charges, but if you think about it for a minute, it doesn't make sense at all in terms of the spatial resolution, because we know there's a massive difference between the average picture, where I would say on average the total charge is zero, versus the fluctuating picture, where in one region I can have a positive charge density as long as somewhere else I have a negative charge density. If I interpret this even in terms of partons, quarks and gluons, if all of this energy is carried by gluons, which it is to a very good approximation, there are corrections to that because these gluons can fluctuate into quark-anti-quark pairs. And even though overall the charges are zero, any of those fluctuations will create non-local patches of positive and negative charge density. So what we did was we took an initial condition generated by the standard machinery that describes heavy ion collisions very well, something like Monte Carlo Glauber. And we said, let me pretend for a minute that everything in this is a gluon. I know in QCD what the probability is. I can calculate what the probability is to split from a single gluon to a quark-anti-quark pair. So we wrote a code, I wrote a code, that has since been vastly improved by all the others who came after me, to take the initial energy density and then sample it to give every patch of energy a chance to split or not split into quarks and gluons, and then uses that to reconstruct what the spatial profile of baryon density, strangeness density, and electric charge density might look like. This is sort of a model agnostic approach. Basically, you give input for how many quark-anti-quark pairs you expect to be produced, and how they're supposed to correlate with things like the energy density. And this algorithm, which we call icing, goes through and samples the initial condition and produces these other maps for you. So this is not a microscopic theory. This is an algorithm that takes your favorite microscopic theory and uses it to produce matching charge distributions to go along with the energy density. This is something that my colleagues at UIUC are working very frantically on right now, and we have a meeting later today to talk about first results where they have taken these initial conditions and plugged it into their state-of-the-art evolution equations for hydro that now also evolve the charge densities. So we are looking in real time at how these initial charge maps expand and evolve with time, and whether that picture of the charge dynamics is compatible with what we usually expect from the energy dynamics. And this is particularly interesting because there are patches of the initial state that have significantly high charge density. Yes, sir.
Yeah, there's a question.
Yes, please.
Should I go to the laptop? It'd be easier.
I can hear you okay now if you'd just like to shout.
Okay, sure. So when you're talking about these other quantities like baryon density, strangeness density, do they have the same sort of nice behavior? You said it's like nature's Fourier transform.
Yes, that is an excellent question. Nobody knows for sure, but we are testing that now. One of the very interesting exercises theoretically that we've done is try to predict from first principles what quantities should be the good estimators, the good predictors of charge-dependent final state flow. So I'm thinking about here something that knows about the difference between positive and negative charges. If I do a theory that only knows about the energy density, that's a C-even theory. It can't tell the difference between pi plus and pi minus. So if I look at the collective flow of pi plus minus pi minus on an event-by-event basis, that C-odd quantity can never come from the C-even dynamics of the initial state. You have to have some charge-dependent C-odd effects. So part of what we've done is we went back to the first principles argument based on length scales that said, why is it that these initial state Fourier harmonics of the energy density are expected to be good estimators for the final state? And we've repeated that calculation now to select on the C-odd quantities. So we have new candidates that are not the usual ellipticity of the energy density. They are interesting mixtures of the energy density and the charge density to create a C-odd combination that we think, based on the same principles that make it work for the energy density and give you this, we think should be good predictors for a charge-dependent flow in the final state. But the answer is nobody knows yet, because the hydrodynamics that can actually do that evolution, including the charge, has not existed until now. It just now exists for the first time, and we are actively testing it. So I'm very excited to find out whether there is or is not a significant linear response or quasi-linear response in the charge sector. Great question. Did I answer it completely?
Yeah, thank you.
Sure, no problem. Cool, so this is one project that I'm very excited about. Oh, here's the better citation, sorry. And this is particularly interesting and relevant for the sectors of the QCD phase diagram that the quark-gluon plasma goes through. If I look on just an average sense, I would say that at very high temperatures, my baryon chemical potential, which tells me the average net number of protons minus antiprotons, or similarly the average baryon density, this would tell me that my average baryon density is 0. That's basically this usual picture. But if I include those fluctuations, you can be in a region that has locally significant baryon density, positive or negative. So the trajectory that you actually take through the QCD phase diagram can be a lot more interesting than just the simple average picture where you say at the LHC, I'm frozen along that mu equals 0 axis. And if I want to learn something about mu greater than 0, like for instance, the physics of the QCD critical point, the only way to do that is to lower the energy of the collision. We think that's not true. We think you can actually learn about the physics of high charge densities at the LHC because you are going through patches of potentially very high charge densities. That's a big advantage because we understand the dynamics of the plasma very well at high energies. We don't understand it well at very low energies, something like the beam energy scan at RIC. So we're excited about this as a possible way of looking for signatures of the critical point even at the LHC, which is something that has not been explored. If you push this even farther, you find that the nuclear systems that behave like a quark-gluon plasma are much wider than the systems where we expect it to work. So we have always expected that the formulation in terms of hydrodynamics as a long wavelength effective theory is always expected to break if the system size starts to get small, if it starts to violate this assumption. So people have long expected that if you take your heavy ion collisions and you go to smaller and smaller systems, that the signatures of the quark-gluon plasma, the jet quenching and the collective flow should turn off. And the big surprise is that they don't. You can go from lead-lead collisions, oxygen-oxygen collisions. The shape and the nature of the event change significantly depending on what selections you make and how you compare them. But even if you go to quite small events, here, this is an example of a proton gold collision. The blue and the red here are hydrodynamic models. And you see that the hydrodynamic models still, even in these extremely small systems that should be far from the assumptions of hydrodynamics, still describe the data remarkably well. This green calculation has a long story with it. That is a non-hydrodynamic calculation, which since has been corrected and no longer agrees with the data so nicely. The shocker of all of this is that hydro still works. These hydrodynamic-based curves still predict the triangular and the elliptic flow, even in very small systems where your assumptions of hydrodynamics are badly violated. So one answer to this could be, hey, hydro works better than expected, and now we go and develop a new theory of hydrodynamics far from equilibrium. Or the conclusion could be, the assumptions that you were making the whole time are questionable. And that questionable set of assumptions starts to get really, really uncomfortable if you push it to very small systems. Because we know that the final state flow is essentially nature's Fourier transform of whatever the initial geometry is. And if you push this down to something the size of the proton, it puts you in a very uncomfortable position of asking, what is the geometry of the proton? And you get a very, very different answer depending on whether you assume that you've got a round proton. In a round proton, you would expect the ellipticity of the proton to be very small, the triangularity of the proton to be very small. And as you go from one round proton to 2 round protons or 3 round protons, you expect a certain systematic pattern of the ellipticity and the triangularity. But I get a totally different picture if I allow the proton to have substructure, to say, oh, the proton should be made of 3 quarks or some quarks and some gluons. Then I totally change this pattern of epsilon 2 versus epsilon 3. So just taking the intuition that we make from heavy ions and pushing it far leads us into this very uncomfortable position of needing to know what is the precise initial state of the proton, even if I believe that what's happening in the plasma phase or whatever the final state evolution is just essentially a Fourier transform of that initial geometry. So coming from a heavy ion perspective, you really need to know what is the actual geometry, the actual microscopic structure of a single proton. And that's what pushes you to the other subfield of high energy nuclear physics, which is cold QCD. How do you measure directly the geometry or other aspects of the structure of the proton? You can't do it by melting the proton. You're changing the system. You have to do it in situ. And the best way that we have to do that is through electron microscopy. And we need the most powerful, most precise electron microscopy we can get. That's provided by a collider. The process is referred to as deep inelastic scattering, but it's essentially just Rutherford's gold foil experiment at orders of magnitude high energy. You send in a beam of particles, in this case electrons, to probe a target, in this case a proton, and you look for events with hard momentum transfer, a backscattered event, where the incoming electron is deflected at large recoil. And the measurement of that recoiling electron, just like the measurement of the recoiling alpha particle, carries exact kinematic information about what you hit in the proton. So you can, just like angular resolved photoemission spectroscopy in condensed matter for electromagnetic systems, you're almost exactly imaging the density of states inside the proton by scattering an electron off of a charged constituent deep inside the proton. So when you do this deep inelastic scattering measurement, you measure a bunch of structure functions. You then extract and interpret those structure functions in terms of densities of quarks and gluons inside the proton. These are called Proton distribution functions. This gives you essentially a one-dimensional picture of the proton as a function of a variable called x. X, it refers here to the fraction of the proton energy or the fraction of the proton momentum that's being carried by whatever you happen to hit inside the proton. When we look at the actual measured microscopic structure of the proton, we see that there are 2 very qualitatively different types of proton. In the region where X is large, this is called the valence region, you see what we usually expect the proton to look like. The proton looks like a dilute system made up of roughly 2 up quarks and a down quark. And we see that in this distribution. We see that at large X, there are primarily up and down quarks. And there are roughly twice as many up quarks as down quarks, just like you expect. Moreover, the location of those peaks, if I take this and trace down, the location of those peaks is pretty close to X equals 1/3. And 1/3 is what you would expect if a proton literally was just 3 quarks at rest. In reality, if you look at the position of those peaks, it's not exactly 1/3. It's downshifted a little bit from 1/3. And that's because QCD is not a static theory. It's got dynamics in it. And so even if you initially had 3 static quarks, each with 1/3 of the proton energy, those quarks bleed away some of their energy into radiation. And so this is the distribution of that radiation, which is primarily gluons, but also quark-antiquark pairs, C-quarks. And we see that there's a huge number of gluons, a huge amount of radiation, but that most of that radiation carries a very tiny fraction of the proton energy. So there are 2 qualitatively different pictures of the proton. the dilute proton, which is what you see when you measure the proton in the large X region, and the dense proton, which is radiation dominated, which is what you see when you measure the proton at very small x. These different regions of the proton change very qualitatively what the structure of the proton should be. The proton spin puzzle, which I mentioned is one of the longest standing puzzles about the proton structure, essentially deals with the question of how is the proton spin, the spin 1/2 of the proton, how is that distributed among the particles inside the proton? And if we take the physics that we know from the hydrogen atom, which is spin pairing, we have a very simple, reasonable expectation for what the quark spin or the proton spin distribution should look like. We know that the hyperfine interaction between the electron and the nucleus leads to spin pairing that wants to cancel the two spins, so that the ground state of hydrogen has hyperfine spin, like F = 0 is the ground state. If you take that physics message of spin pairing, then you would expect a spin 1/2 proton made up of 3 spin 1/2 quarks. You can easily satisfy that if 2 of the quarks are spin paired, and the third quark, which is spin 1/2, gives you the overall spin of the proton. That would be a scenario in which there is 0 orbital angular momentum, just like the S-wave ground state of the atom, and the quarks carry all 100% of the proton spin. Perfectly reasonable expectation, which is totally wrong. When the ENC collaboration actually measured the quark contribution to the proton spin, they found that it's not 100%, it's a lot more like 25%. More recent measurements of gluon polarization show that the gluons are polarized, the polarization is non-zero, and they account with large error bars for about 40% of the overall spin of the proton. Even including that, that leaves a large amount of phase space left for orbital angular momentum of quarks or gluons inside the proton. What this is telling us is that the ground state of the real proton in QCD could not be more different than the ground state of the hydrogen atom. It is not S-wave. It has a significant amount of orbital angular momentum swirling around like a tornado. It has significant positive polarization of both quarks and gluons, maybe even somewhat canceling polarization of different types of particles. So the ground state, the chemistry of the proton is vastly more complicated and vastly more interesting than the structure of the hydrogen atom. That's not the only puzzle about the structure of the atom. That radiation-dominated region somehow finds a way to keep squeezing in more and more radiation as you go to small x. This can't continue forever. You cannot literally take these trends and extrapolate them to infinity. If you did, you would violate unitarity. You would literally squeeze more density into the proton than can fit, such that probabilities get greater than 100%. You violate probability conservation. So it cannot be the case that I can just squeeze in more gluons as I go to smaller and smaller x, and I have more and more radiation. What has to happen sooner or later to be consistent with the principle of probability conservation, unitarity in quantum field theory, is that Bremsstrahlung, radiation of extra gluons that starts off at low energies or relatively large x, has to slow down and eventually saturate to a constant maximum density due to detailed balance between radiation of more gluons and reabsorption, recombination of pre-existing gluons. You can describe this saturation effect in different ways, in different approximations, but the mechanism itself is universal. There must be nonlinear high-density interactions that regulate this behavior, that regulate this growth as you go to small x. If you don't, you break probability conservation and you can't do anything with the theory. This is a really exotic state of matter which is predicted to exist, where this saturation begins to set in. It's a gluon-dominated state of matter, which essentially is like a gluon laser. It has the highest intensity of gluons allowed in nature. Like literally, you cannot fit any more gluons in here. They just get reabsorbed. So it's a very exotic state of matter, similar to, say, the Schwinger limit of QED. So given the outstanding puzzles about the proton, we need a new tool to answer these puzzles. And that is currently being funded and designed and constructed in the US as the Electron-Ion Collider, the EIC. The EIC is a next generation nuclear physics machine. It will be built as an upgrade to Brookhaven National Lab in Long Island. And it's designed to answer both of these essential questions. The questions about what is the spatial and momentum structure of the proton, including how is the proton spin distributed, and can I see with any clean electromagnetic signal evidence of that theoretically predicted but never confirmed state of saturated gluon densities. Those are the things we expect to see at the EIC. We expect to see proton structure with unprecedented imaging. We expect to see gluon saturation, at least first hints of it. But in my mind, the most exciting prospects for the EIC are the things we don't expect, the things which are interactions between these two different disciplines, which for decades have evolved in parallel with not that much crosstalk between each other. So the things that I am most excited about for the EIC era are things like the theory of spin at small x. The theory of energy density, or total number of gluons at small x, has been well understood for decades. But I am fortunate to have been involved in computing the analogous behavior of spin-dependent distributions at small x, which was not known previously. We derived the evolution equations, we solved them, and we saw that these quantum equations governing the small x behavior of spin predict enhancement of the total spin coming from quarks at small x, also a much smaller enhancement of gluons. So we are currently continuing to build on this train of work to try to study phenomenologically what is the contribution to the total proton spin coming from the very low X region, where you always have to extrapolate beyond where the data stops down to X equals 0. Another really exciting opportunity for overlap is the ability to continue the small system story from heavy ions. In heavy ions, you can only collide hadrons with each other. Nature only gives you hadrons down to a certain size. You get a proton, and that's about it. If you're clever, you might be able to construct a pion beam, which would be a bit smaller in size than even the proton, but you can't go any smaller than that with stable particles. The EIC, however, which uses an electron beam and therefore interacts with a photon, has the potential to select on even smaller size systems. Because that photon is not a static photon, it can fluctuate into a quark-anti-quark pair, and that QQ-bar pair can have whatever size you want. Moreover, you can select experimentally on the typical size of that dipole configuration just by selecting on the degree of recoil of the electron. So at the EIC, you have the ability to make as small a system as you want just by selecting on the Q squared of the electron. So if I buy it that something hydrodynamic is happening even in very small systems, you can continue to explore the behavior of small systems to infinitely or arbitrarily small systems just by going to the EIC and selecting on these dipole configurations. So if the quark-gluon plasma signals have not turned off yet in proton collisions, you can go to something even smaller than protons. I know I'm out of time, so let me just summarize. This is a fantastic time for students to get involved in nuclear physics, because right now we are at the apex of the quark-gluon plasma and heavy ion collisions. We know that the quark-gluon plasma is created. We know the canonical signals of the quark-gluon plasma, but there are still a couple of very interesting open questions about how far one can push it. So we are right now at the apex of the heavy ion discipline, and we are right now setting the groundwork for the next decades to come with the EIC. As I mentioned, the EIC will capitalize on investments made. It's designed to solve both the proton spin puzzle and the discovery of gluon saturation. I am happy to report that this is actually happening in real life and that money has been committed and is being spent to actually do this. So the US Department of Energy has granted what are referred to as critical decision milestone 0 and critical decision milestone 1 to the EIC. Those are the official markers that track how close we're getting from the idea of the EIC to actually turning on the machine. So the current projections expect the EIC to turn on somewhere in the vicinity of 2030. So for a student, now is a fantastic opportunity to work with real data that we have on tape in abundance for heavy ions, while setting yourself up for the future to come when you will be ready for faculty positions yourself. And I just want to close on this message that when I was a student, when I was a postdoc, I was really worried for a long time about getting scooped, about getting things calculated fast enough to beat somebody else to it. And over the years, I've slowly come to realize that there is an infinite amount that we do not understand about QCD. And so it doesn't matter about the solution to one problem so much, because there is discovery enough to feed us all for a lifetime. And if you solve a particular problem before I do, great for you. There's a million other problems out there that I can work on too. So I think this is a great opportunity, like I said, for students to get into the field, and you have more than enough science problems to work on for your entire career, you and me both. Thank you very much for your patience. I'm happy to answer any questions.
Okay, super. Thank you so much, Matt. A few people are quickly running just because they have other commitments at a similar time. And also, especially for those who were here at the beginning, thanks very much to Matt for talking at 5 a.m. Las Cruces time. Yeah, are there any questions from the people who are remaining? Yeah, please go ahead.
I had one, but I think it might be a stupid question, but that's fine. It was just on the details of the EIC collider. You said that you're going to measure the properties of the gluon saturated proton electromagnetic.
Yes.
What is the actual interaction? Is that looking at like QQ bar pairs produced by the saturated gluons, or is there something more complicated going on there?
Yeah, so it's both. There are two main ways that you can measure the gluon distribution specifically. So maybe this is what you have in mind that, oh, let me go to, which picture do I want to show? This one, here we go. So at leading order in QED, the primary mechanism by which DIS occurs is a direct interaction of the photon with the quarks that are inside the proton, coupling directly to the electric charge of the quarks. So at leading order, DIS doesn't see gluons at all. It interacts and it only directly measures the quark distribution. What one normally does to infer the gluon distribution from this is you obtain the gluon distribution from evolution corrections, most commonly at large X by DGLAP evolution. So you measure the PDF at one value of Q squared, you measure the PDF at a different value of Q squared. Those Q squareds, by the way, are just selection cuts on the hardness of the electron recoil. So it's just different event selections. And you can relate the PDF that you measure at one value of Q squared to the PDF that you measure at another value of Q squared. And they're related by an integral, which is an integral over various PDFs, which includes the gluons. So the standard way to obtain gluon information from DIS, especially at large X, is through DGLAP evolution, which requires that you have a good lever arm in Q squared so that you can select on that logarithmic dependence of Q squared here to extract information about the gluon distribution there. At small x, however, the mechanism of DIS changes, as you alluded to. At small x, the dominant mechanism is not a direct interaction of the photon with a quark, primarily just because at small x, you don't have quarks to knock out. You're not really kicking out valence quarks from the proton because there really aren't any of them at small x. So instead, what happens primarily is an NLO effect where the photon fluctuates into the quark-antiquark pair, and then you have essentially a hadronic scattering of the quark-antiquark on the proton, and that mechanism measures the gluon interaction directly. That's a very sensitive probe of the gluon densities. So it's a different formalism for how to extract the gluon density. There might be a little bit of systematic error in the conversion between, let's say, the dipole amplitudes that one standard usually extracts from small x and the gluon distribution, but they're very closely related to each other. Yeah, good question.
Other questions?
So Matt, I expect you'll talk a little more about your upgraded hydro next time around. So what can you give me an idea of what the timescale is until you said you're working on it? So when do you expect to see results?
For the EIC, or you mean for the BSQ
from your
hydro evolution?
Yeah, from your upgraded hydros with fluctuations.
I am hopeful that when I have a meeting with Jackie and collaborators at 12 p.m. this afternoon, that they will show me preliminary results. They've had the hydro part running now for several months over the summer. The last sticking point was making sure that they were handling charge-dependent freeze-out correctly. And I am told that as of the beginning of this week that is now working, and that they are collecting preliminary results today that hopefully we will talk about and see whether the estimators are or are not correlated with that flow. So maybe I can show you something preliminarily next week.
Okay, absolutely hot stuff. That's really that actually is absolutely cool because it gives you a totally different angle on things.
Yeah, thank you. We were very excited about this. I think the onus has been really on us up to this point to show that this could have some effect. And if you're just looking for like the usual observables, V2 of all charged particles or something, probably you're never going to see this.
Yeah.
But that was what was so interesting to me, was sort of using this idea of spin asymmetries. You know, I got my exposure to time reversal odd quantities like transverse spin asymmetries. And so that was what sort of pushed me in the direction of, well, if I select on something that is C odd, then I can be safe and I can be certain that the usual stuff doesn't contribute to it at all. So I should have a good handle, hopefully, of selecting on this new stuff.
This is really a cool idea. I love it.
Thank you.
How would being close to a critical point change the amount of fluctuations and the impact of those fluctuations?
Oh, are you talking about the amount of fluctuations like at this level in the initial state, or are you thinking about thermodynamic fluctuations later in the evolution?
Yes.
Yes. The part that I think I can say something intelligent about is the thermodynamic fluctuations at later times. That Jackie and collaborators have done some preliminary work now that show the range of trajectories that you can get. If I take an initial state made up of this in our model, and I just plot the trajectories of every single point in or every single SPH particle for her through the phase diagram, you find that there is a huge spread of initial conditions, and that spread of initial conditions kind of evolves. It sort of gets narrower as a function of time. So you get some spread, let's say, at the point when different points in your event are going through the phase transition. Some of them will be closer to the critical point than others. At that point, you may have very interesting critical fluctuations. I mean, I don't know. It's wide open to say phenomenologically what's going to happen to my final state observables if I allow all of my points in my hydro to fluctuate differently, and some of them may experience large critical fluctuations. Hopefully we'll find out within the next 6 months or a year, because we have now all the tools to investigate that. As far as fluctuations in the initial state and critical point things related to this is where I need to take a step back and really say that this is not a microscopic model of what's happening in the initial dynamics. This is a way of reverse engineering. If I only have an input of this, reverse engineering what the other maps should be for some reasonable assumptions, but it is not a real like time-dependent calculation using microscopic CGC about how these quarks should be produced as a function of time. That's a much harder calculation. All we're doing here is sort of reconstructing the expected number with the expected spatial correlation. So this is what a typical event could be, but I don't think I can credibly say anything about dynamical fluctuations in the early time, especially about things related to equilibrium, non-equilibrium, critical phenomena, things like that.
Well, right, having fluctuations in the game to see if they leave a trace is already a huge step up to having none.
Maybe my headphones are not passing things through. Let me turn this off.
Right, just having fluctuations in
sorry,
there.
can you say something? I just want to make sure I'm hearing you.
Yeah, we're saying things. Can you hear us?
No, it's still not coming through. Crap, let me
No.
set my Zoom.
Yeah.
Oh, okay, now it's coming. I hear you. Sorry.
Okay, now what I just said is having fluctuations and being able to check whether they leave a trace anywhere is better than having nothing. And
Exactly.
Right? I mean, you can give people a reason to look for these more complicated things to actually construct this with more dynamics and more physics input. And if you find out they don't do much, then okay, but then there is not much motivation. But I hope it will provide.
That's right. So that's exactly our purpose at this step of the game, is to show that this effect could matter for something, that it could be measurable for certain set of observables, hopefully to propose a new set of observables that could be used to measure such things, and then yes, go back and then carefully revisit all of the assumptions of the microscopics. That's part of what I think is nice about this model agnostic approach that we've taken, is that the particular calculation shown here uses a very simple dilute dense CGC calculation as the input for how to get the expected number of QQ-bar pairs out of the expected number of gluons. But you can take some different assumption for that. You could take thermal abundances, you could take your favorite non-equilibrium model, you could take dense as opposed to dilute dense, which was just a matter of convenience. Ideally, we would like to encourage people to use that now open source modular framework to plug in whatever microscopics you want. This initial state, by the way, is open source and ready to go. You can pull this off of GitHub and do what you want with it right now. It's the hydro evolution, which is the new component.
Cool. Okay, super. I actually have one question, which was from close to the beginning, where you talked about QED and the high precision of QED.
Yes.
Which was just, it was interesting because you talked about the here we go, 1 part in 10 to the 15 combined uncertainty, which I've been aware of. But then there's this comment about 1100 digits of precision further down, which just seems kind of silly if you only have 15 digits of precision from I guess the experimental uncertainty. Or am I thinking about that the wrong way?
Well, the observables here are a little bit apples and oranges here. The theory is being done for G-2, which is about as clean as you can get theoretically. Here, the experimental uncertainty is on the cesium-133 transition. So I expect that this uncertainty is probably limited by multi-electron complicated nonlinear effects, whereas this one is much cleaner theoretically.
Yeah, I also thought, okay, fair enough that your quoted uncertainty there is for the cesium flopping. I thought that also the G-2 was a similar level of uncertainty in the experimental measurement, something like 10 to the 15.
Could be. I'm not sure. That's a good point.
Yeah. Okay. Super duper. Last question before we wrap up. I don't think so. All right. Thank you, Matt. Really appreciate you getting up super duper early. And looking forward to your talk next week.
And thanks for pitching it at a level that should have been really good for these guys.
Yeah.
Absolutely marvelous. Absolutely marvelous talk.
Thank you so much, sir.
That's great. Thanks, Matt.
No problem. Thank you for coming.
Thank you for the great talk, Matt.
Thank you.
Thanks very much, guys. All right. I will see you next week then.
Absolutely.
Take care. Bye.
Thanks, guys. Bye.